Okay, looking at the time. So suppose in this example, we're going to use 5 one-dimensional data points. So this is our data points. 1 to 6 is class 1 as one class. So 1, 2, 1 to 6. 6 is actually x5. So y5 is 1. So this is one group, and 3 and 4, this is confusing, is the other group. So this 2 data belongs to a group, one class, and this 3 belongs to another class. Okay, so we're going to use polynomial kernel with degree of 2. Again, this degree is something that you can supply as a hyperparameter. And we set the cost factor to be 100. So the first step, we use our maximization function to find alphas for our 5 observation. So this is exactly the same thing that we copied before, except now we replaced those indexes with real numbers. And as you notice here, we stopped using the direct dot product, but we use the dot product of after the transformation. So we're going to send this optimization problem to a quadratic programming solver, and which going to actually give us the result. So we don't have to do the math. So here, the result tells us all the alpha values for every of the 5 data points that we have. And we observe that alpha 1 and alpha 3 are 0, so those are not support vectors. 2, 4, and 5 are support vectors. So 2, x2, x4, and x5, those are our support vectors. So now we need to, after we finding alphas, we can actually work out our discrimination function, decision function. I called it decision function before. Here, giving a new example how we're going to classify this. So we use this formula, we plug in what we have received from our quadratic programming solvers. So we have 3 alphas that's not 0. So those are the 3 terms that we have here. And we add the b. We don't know b yet, but we can find this out quite easily. So this is our alpha 5. This is the term here. The y5 has class label of 1. Some others have class label -1, so it's here. This is our, again, kernel function after we applied z with x5. So this gives us the discriminant function as such, but now we need to find out b. We know for those support vectors are sitting on those boundary lines. So we know the boundary lines equation is this for the positive class, and the other is for negative class. And we can plug in our x2 to this function to find b. We can do any of those. 5 or 4, they're going to give us exactly the same result, and we find b is 9. This gives us the final discrimination function. So if we draw this here, what you can see, this discrimination function does actually separate class 1 from class 2 very clearly. Those 2 points, if we think of if we imagine those points in the feature space, those 2 going to map to here on the curve, and those 2 points going to be mapped here in the feature space on the curve here, and 6 there. So you can see we can actually, a straight line could separate one class from another. Okay, do we have questions so far? Okay. So when we use support vector machines definitely need you to normalize your data. It's critical. And actually, I think most of the support vector machine implementation does normalization by default for you. You can, most typical is to min-max to 0 to 1, but there are other alternatives. If we have categorical data, you will see that support vector machines in the R application implementation, it does one-hot encoding for your categorical data. So you're going to end up having lots of dimensions. So the kernel parameters, we look at the C and we look at the Y, and we noted how what's the effect of setting large and small C and gammas. I call it Y, yeah, it's gamma. So generally, those are searched in exponential factors. For C, you can try out those numbers. For gamma, you can try out something else. So in R, I mentioned in R implementation, gamma is used. In some other implementation, sigma was used. So you have to actually be careful and see what is actually used in the implementation to decide how to set your values. I mentioned this point before because the support vector machines, if your minority data actually contains the support vector machine, your classification performance is going to be actually pretty good. But a lot of times, you cannot guarantee your minority data contains the support vector machines. And in our experience, that support vector machines is actually quite sensitive to data class imbalance issues. So if you do oversampling or undersampling, like what we described earlier, it often going to improve the performance of support vector machines. Later today, we're going to talk about, so far we explained support vector machines as a binary class classifier that it separates one class from another. But support vector machines can also be used to classify multiple classes. And we can all look at some of the methods later today. I don't know if we're going to have time to look at our R code on police shooting data today, but I included this part in the lecture note in order to extend two concepts. One is bias, another is variance. If you read outside of the textbook, you will find bias and variance being used in characterize the performance of machine learning algorithms. So bias means this model learned is not flexible enough. It underfits the data. So the performance is very low when you have a biased, when you have a model that's highly biased. Variance, on the other hand, they fit the training example too well that you can expect its performance going to vary a lot when you use it on a different data set. So such model is called high variance model. So I did a set experiment using different cost and gamma values to illustrate this idea using support vector machines. So to prove to you that when you have high C, very high C, you're going to often have high variance. When you have high gamma, you're going to also have high variance performance. Do I have questions on this slide? Okay,